Say you like to draw. Specifically, say you like to draw sports cars. What about the spoilers in the back? Do they impact the car's performance, or are they there just for show? Okay, say we have two cars now. One has a spoiler and one does not. If they were racing under the same conditions, same engines, and same route, the one with the spoiler would actually win. What if we add a third car with an airfoil? Which one do you think will win the race now? Well, in order to understand the differences that makes one car faster than the other, let's take a closer look at the main forces, lift and drag, that are acting on the car. Lift and drag are forces created as air flows around different shapes. Let's look at a cross-section of an airfoil or wing to clearly show these effects. Air flows around the wing smoothly, except at the tail end where there is some swirling air. The smooth, steady air is called laminar flow, while the swirling air is called turbulent flow. Laminar flow consists of smooth, parallel lines, while turbulent flow has chaotic swirls. Pressure is defined as force divided by area. However, since we are most concerned about the forces of lift and drag, it is easier to write the equation as force equals pressure times area. Pressure differences between two surfaces of an object creates a force going from high to low pressure, because the pressures want to equalize. Let's identify the areas of high and low pressure. The air travels faster above the wing, creating an area of low pressure. Conversely, slower air on the bottom of the wing creates a high pressure area. The airflow above the airfoil separates toward the back and creates turbulence, impacting lift and drag. Now that the high and low pressure areas are labeled, it is easy to identify the forces of lift and drag. The high pressure area below the wing and low pressure area above it creates a force called lift. The high pressure area at the front of the wing and a low pressure area at the back creates a force called drag. Drag pushes the wing backwards, while lift pushes the wing upward. If we take the same airfoil and tilt it upwards, it creates greater pressure differences and changes the area of the wing that the pressure acts on. If you remember the equation we talked about earlier, both the area and the pressure affect the force. This is why it is important to determine the best angle for the airfoil to generate the optimal amount of lift and drag for your application. Airfoils on cars use the same principle but are flipped upside down. A drag force is still pushing the wing back, but the high and low pressure areas have been switched. Thus a downforce is created instead. Minimizing lift on a vehicle is important because it causes the tires to lose traction. Less traction causes bad handling and slower accelerations. Airfoils use a downforce to push the back of the car down. Let's take a closer look at these effects on sports cars. Say air is flowing from right to left. The basic airflow around the car would look like this. Air approaches the front of the car, traveling in laminar flow. As it goes around the car's body, the air separates at the back of the car, and parts of the flow become turbulent and swirl. The flow in the back is an area of low pressure, while the shaded regions on the front and bottom of the car represent areas of high pressure. The pressure difference between the front and back creates drag, and the pressure difference between the top and bottom creates lift. Now let's look at the car with the spoiler. The airflow around it is similar, but with key changes in pressure differences. When the air hits the spoiler, pressure builds up, causing a decrease in lift. The flow is then deflected upward, which increases drag. However, the advantage of less lift is greater than the disadvantage of more drag, so the spoiler will improve the car's performance. Instead of using spoilers, we can use an airfoil that decreases lift without increasing drag. Air flows around the car, but this time a localized pressure difference at the airfoil creates a downforce that doesn't block the airflow like the spoiler. Lift is decreased without significantly increasing drag. In order to test these principles, we built a small wind tunnel. Wind tunnels are usually large and have a controlled current of air or smoke moving through them. Here's the setup. At one end is the nozzle where the smoke is introduced. Next to it lies the test section where the object of study is placed. The fan in the back pulls the smoke out the other side. When performing the experiments, we use lights to illuminate the test section. It is important to redirect the light in the wind tunnel to create a good contrast between the smoke and background. In this empty wind tunnel, you can easily see the flow. From the nozzle to the test section, you can see the smoke accelerating and flowing smoothly through to the other side. Now let's get down to the fun stuff. We chose a 1/24th model Porsche Carrera to test because it's a high-performance sports vehicle that I would like to own someday. Take a look at the streamlines. The smoke flows smoothly over the front of this gorgeous machine, but eventually becomes turbulent at the back of the car. Slow motion really captures the path of the turbulent airflow. Let's see that again. Nice. Next, we tried looking at the effect of a spoiler on the Carrera and how it blocks the flow over the rear of the car to create a high pressure zone. Air flows over the top of the car and eventually hits the spoiler. After hitting the spoiler, the air is deflected in two directions. Some of it swirls backwards, while the rest is redirected upwards. The redirected air leads to a lower pressure zone behind the car, which can increase drag. However, the deflected air that creates the high pressure zone over the trunk reduces the effective lift with a downforce. In other words, your car will be able to accelerate faster and handle better. Next, we have an airfoil that demonstrates the effects of pressure difference and their relation to lift and drag. The smoke sticks to the airfoil until it separates near the tail. The area under the flow separation is lower pressure because there are only small amounts of air there, which causes the air above it to expand and fill the space, creating turbulence. The slower airstream moving under the airfoil creates a higher pressure zone. We can see a cooler visual when the airfoil is tilted and the effects of the airflow become more pronounced. The flow over the top of the airfoil expands into a bigger area, creating more turbulence and low pressure zones, while the bottom of the airfoil blocks a greater area of the airflow, leading to higher pressures. Drag and lift change dramatically compared to the airfoil with the low angle of attack. You can experiment with the effects of lift and drag by sticking your hand out a car window and adjusting the angle. Now let's get back to the sports cars. Here we have a Lamborghini Diablo for your viewing pleasure. It features an airfoil on the back that acts like an upside down wing. This creates downforce without significantly impacting drag because it allows the air to flow around it instead of blocking the flow like a spoiler. In slow motion, you can easily see the flow separating when it hits the airfoil and that the turbulence occurs further away from the rear of the car compared to the Carrera. Back to the drawing board. Let's review what we've learned about tricking out sports cars. We found that an airfoil provides the best solution to decrease lift and drag on your car. It looks cool and will give you better handling, faster acceleration, and higher top speeds. Now we can clearly see that if these three cars were to race along the same track under the same conditions, the car with the airfoil would win because of superior aerodynamics. The one with the spoiler would place second. Fun fact, at 130 kilometers an hour, F1 cars can generate more downforce than the weight of their car, allowing them to theoretically drive upside down in a tunnel. Do not try that at home.